Hello everybody, welcome back to our lecture series on satellite communications. Today we have our second lecture on antennas, and today I would like to look deeper into receiving antennas here and into the so-called Friis transmission formula. There are only a few aspects left. Once we have all these aspects in our portfolio, we can use them and practice. Talking about receiving antennas is actually something which is really similar to the transmitting antennas. Antennas are, as we know, reciprocal. That means any antenna that can transmit can also receive. And even more, a transmitting antenna behaves exactly identical to a receiving antenna. That means when we have the radiation pattern for the transmitting antenna, the radiation pattern for the receiving antenna is identical to it. This is a consequence of the so-called reciprocity theorem in electromagnetics. I do not want to get into it, just believe me, you can use any transmitting antenna as a receiving antenna and vice versa. That said, this also means that when we switch our complete transmit-receive path, nothing changes at all. I will come back to this later. Okay, and now let's look at the receiving antennas. When I have a receiving antenna, I have an antenna somewhere in space, and into the antenna there's incident an electromagnetic wave. This electromagnetic wave is caught by the antenna and it's transformed into received power here. So any power that, well, the transmitting antenna transmits, for the receiving antenna, the power is received. That said, means that an antenna like this acts like a source with a voltage here and an internal resistance. And the internal resistance is identical to the radiation resistance in the transmit case. Okay, but we are not going into the circuit level of antennas. That's why I don't want to talk more about it. We want to look into the system level of antennas. And when we look at an antenna from the system standpoint, an antenna is nothing else but a big fishing net for electromagnetic waves. When we have a wave coming in here like this, and this wave has a certain power flux density S. And we can think about an antenna like, as I said, a fishing net. And let's do it here like this. I set up here a frame, and some of my power actually goes through that frame and some does not. And the part of the power that goes through that frame is collected and put onto a connector. And that means all the power flux density that goes in is eventually at the end of the day at the connector. And since we get from the connector, we get a power P received, we have to relate this to the incident power flux density. The power flux density is given in watts per square meter because it's a flux density, whereas my power is given in watts. That's our first hint that we have to do some kind of conversion. And just looking at it, you see that, well, since this is a power flux density and there's some area here like this area here, we can say that the power flux density that is caught up by this area A is the total power received here. We can say PR is power flux density S incident times my area A. This area A is not necessarily the real area. It's a so-called effective area. That's why we call it AE, or sometimes also known as the effective aperture. So. And from that, we get this very simple but very powerful formula. Received power is equal to my, is equal to the power flux density incident times my area A of the antenna. It has to be clarified what the area of an antenna means. For antennas like this, so-called horn or pyramid antennas, it's straightforward. For other antennas like wire antennas, it's not necessarily. And once we know that, we can define actually our so-called effective aperture. Yeah. Backwards, no? When we know what the received power density is and my received power, then the ratio between the received power and the received power flux density, that is my effective area. Just going back here, it might be the physical area, but this may differ, no? And this becomes obvious as we, when we look into, when we look into these pyramid antennas, let's make it in black. When we look into this pyramid antennas, or something similar like this, then, as I said, this may be this area here. In case of a parabolic antenna, with this parabolic dish here, we have this so-called primary feed, and then my area is basically the area of the dish, because there's an incident flux density. This is reflected and goes in here. So we collect the area of the dish. However, some of my flux gets a so-called spillover like this, and same here, no? So-called spillover effect. That's why our effective area is not necessarily identical to my physical area. It's usually a bit smaller. And when we deal with wire antennas, let's say this is my wire antenna here. Then our effective area has basically nothing to do with the physical area, because there's a wave coming in here, and actually the wave is sort of sucked up by the antenna, the S of the wave. That's why here for wire antennas, the physical area has nothing to do with the effective area. Ideally, the physical area of a wire antenna is 0. That makes it difficult to define over the physical area. Here's a very typical picture shown in many textbooks. You can see that there's now the incident wave is coming from the right, and down here is my dipole antenna. And you see the dipole antenna catches waves or flux lines from the incident wave from a certain area in front of it. And this certain area in front of it is this area here. And that's the effective area of a wire antenna. Calculating the effective area, you will see it's very easy in a few seconds. And also there are tables on Wikipedia and so on, and in my lecture notes to find the effective area of a dipole. I'm missing here one slide. Do I? Yeah. Sorry about that. I'm missing one slide. Okay, let's put it here. It's gone for some reason. This slide is the so-called efficiency. The efficiency is called eta F or antenna or whatever. I call it eta efficient. It just relates my effective area or effective aperture to the physical area. That's all. That's why it's a simple slide that's missing. That's why you can just put it here. And as you have these spillover effects here, your efficiency for dish antennas and so on is typically, well, maybe something like 60% to 90%. So the physical area must be a little bit bigger than the actual efficient area, which is in the range of something like that. For wire antennas, this is totally different. Okay. There's an extremely, it's not simple, but there's a relation between the effective area, AE, and the maximum gain of an antenna, or the gain of an antenna. Remember, we defined the gain last time, so many dBis and so on. The bigger the gain, the bigger the effective aperture. So my effective aperture is always proportional to my gain of the antenna. High gain antennas in transmit case are also high area antennas in the receive case. And one twist comes to it. It's related by the frequency over this factor lambda naught square. So when the lambda becomes small, the effective area also becomes small. So the higher the frequency, the smaller the effective area, which is not a big issue because at higher frequencies we need only smaller areas in order to get the same gain, as we'll see when we do some calculations. That said, you know that for higher frequency antennas, the antennas are smaller in physical size than for lower frequencies. Remember the antenna I showed you last week, the huge parabolic dish antenna in Usingen, and this antenna, and I don't want to go through all the slides back here, has a diameter of, I think, something like 30 meters. And that makes the effective area extremely big. When the effective area is big, also the gain is big. This antenna has a typical gain of a few millions. Okay, so keep this formula in mind because that's something we need often. Because usually when you buy an antenna, the gain is given but not the effective aperture, for the simple reason that the effective aperture is depending on the frequency. Well, let's have an example here. From our antenna I showed you last week, we remember we had a gain of 104. This is antenna operates at 3.3 gigahertz. And from that we can easily calculate the lambda naught is C over my frequency, which is 0.091 meters square. There's a square missing here. No, sorry, not square, sorry. It's just meters. No? Square is the next line. And then plugging it into our formula up here, we get the gain, lambda naught squared divided by 4 pi. We get some area which is 688 square centimeters, which is basically like a box of the size 26 by 26 centimeters. Roughly the size of a A4 paper. That's my collecting area of that antenna. And I do not have a photograph of the antenna, but this is roughly the size of the antenna itself. That's why the antenna is roughly identical to the physical area. So, okay. And with this equation, we can now do the following. We can get the received power, which is should be here. That should be an R. This should be all R's. Sorry. The received power is, well, from what we know before, no, the collecting area times my incident flux density, and I can replace now my A by my formula here, G times lambda square over 4 pi. And then maybe let's write it down again. P received we can also write as power flux density received times my gain times lambda square over 4 pi. Okay. Good. Well, here's my slide with the effective aperture. It's for some reason went down. I explained this before. My eta is, let's go back here. My eta is my effective area to my physical area, as I explained. No? And typical value is 90%, or I said 60% or so. Which I have explained already. Okay, good. Now we know everything about transmitting antennas. We know everything about receiving antennas, and now we can combine these two. What happens when we have a complete link? And that's the all exciting step here. No? Let's take at a complete transmission chain here. We have a transmitter on the left and we have a receiver on the right. In between we have a wireless link with a distance r. There's only air or basically nothing between. Now, how do we get our P received from our P transmit? Basically, how do we get P receive, the red P receive, given the P transmit, the gain of the transmit antenna, the gain of the receiving antenna, and the distance r. And we have everything in place now to calculate that. We can start with the effective area here, or we can actually, before we do the effective area, let's calculate the incident, green, the incident power flux density S here. No? So this S is, as we know from our transmitter formulas, my P transmit, let's put it on a fraction, my P transmit times my gain of the transmit antenna, remember last week, over 4 pi r square. That's my S. Also we know, let's do it maybe in blue, that my P receive is my S times my effective area. So this is the same, so I can replace that. P received is P transmitted times G transmitted times 1 over 4 pi r square times AE. AE, remember, AE is my gain of the receiving antenna times lambda naught squared over 4 pi. So I can replace this as well. Then we get P received is P transmit times G transmit times 1 over 4 pi r square times G received times lambda not squared 1 over 4 pi, just plugging that in. No? So now I have my received power only for values which I usually know. My transmit power, my gains, and my distance and my frequency. Let's rearrange that such that we see it more clearly. P receive is equal to P transmit times my gain of my transmit antenna times my gain of my receiving antenna times, so now all of that is left over, lambda naught squared over 4 pi is 4 pi squared and r squared. No? So I can put all of that in a big square. This is known as the Friis transmission formula. By Mr. Friis, set up, I don't know, 1920s or so. Extremely powerful equation. Let's look again. No? Here I have my P transmit, gain transmit, gain receive, I know, frequency, distance, and then I get everything. Okay. Here I just put it together and nicely written. You can see the formula again. It's worthwhile to memorize that formula. Often this formula is given in log scale. That's also interesting. Let's make it maybe in blue. And when we give our transmit power in dBm, then we can find the, well, that's basically also the EIRP. No? Then we can find the transmit power times gain on logarithmic scale is just adding the two. No? And now this has to be given in dB, or as we usually say, in dBi. No? And the same we do for the receive gain. Just adding these things, and now I have to add this last piece here. And this in dB, well, is 10 times log, or when I put the square on the other side, it's outside, I can say 20 times log 20 times log 10 of my lambda over 4 pi r. And this is equal to my received power in dBm. Everything is now in dBm. Okay. That's exactly the same, just as everything expressed in dBm. We have an example in a second. No? So here's a nicely written way of the formula in dBi. That's also a Friis formula, but this time in dBi. And there's a plus missing, I just see. So I don't know what's missing. Okay. Often this part here, is related, which is related to the distance of the antennas. No? Is called the so-called path loss. As this factor here makes the number very small. And we can put this together in this 20 times log lambda over 4 pi r square. And this is actually the path gain, to be precise, because it shows me how much my power becomes bigger. This is a number much smaller than 1. And we can just use the reciprocal, and then this is called the path loss. Or sometimes also called free space loss. And that's my attenuation. A path is equals to 20 times log 4 pi r over lambda, which is 1 over this, and then the square can go to the front, and it's not 10 log, it's 20 log, and then the 4 pi r is in the numerator, and the lambda goes into the denominator. And just replacing this part here with my path loss, I get a new version of my Friis formula, which is this. It's the same as before, but I just replaced my path loss with minus, because it's 1 over this. And again, there's the plus minus sign missing here. So, okay, that's my Friis formula. And the Friis formula is our friend for calculating a complete wireless communication link. When we know the two antennas, we know the transmit power, and we know the distance, and we know the frequency. So I have an example here. Let's make a small stop here.